Okay, so here's where we were last time. We were talking about line integrals of vector fields, and it came about from looking at a particular physics application, the question of how to compute work, right? So, we have this formula from chapter 12, but this makes certain assumptions. It assumes your vector field's constant. In the real world, that's not the case. It assumes that your displacement is along a straight line path. Again, not so much in the real world, right? So we consider the case of non-constant vector fields over non-straight paths. We take our usual chop it up, add it up strategy, and what we ended up with was that we were adding up a bunch of things that look like this. We were adding up over the entire curve, and those little dWs being computed by something that would be natural to denote like that, we find ourselves looking at this expression here, right? And so this is called a line integral. It's very often called a line integral. Of course, you all recall that we already have another expression for which we've used the term line integral. Right? So you may recall as well that when we talked about the first kind of line integral, I indicated I like to call it a scalar line integral because the integrand's a scalar. Here, I prefer to call this a vector line integral because the integrand is a vector, or really perhaps more to the point, because the differential is a vector. Okay, all right. So we talked about how to compute such things. It's the same kind of a pullback we did for scalar line integrals. Did some examples, right? And so we're going to pick up from there now. Now, I do want to come back to this just for a quick moment. There's something about this example that's counterintuitive if you really sort of think about what did we just compute here. We just computed the amount of work that it would take to accomplish a certain task, and we got a negative answer, right? So that's weird. Right? I mean, if it takes a positive amount of work to do something, I'm going to have to exert a positive amount of work. I could imagine that I've got some sort of a power tool that's going to do it for me, or I'm going to, my car's engine is going to, help me drive up that mountain, whatever, right? And a positive amount of work means, well, I'm going to burn a positive amount of gas, right? Can you burn negative gas? So not exactly, but there is a relatively modern, at least in the scale of my life, not so much your lives, right? But in the scale of my life, a relatively modern engineering design creation that actually is the perfect metaphor for explaining this, and it's hybrid cars. So hybrid cars, they burn gas, sure, right? But they also have a battery, right? And you've got a sort of a battery level at any given point, and as long as the engine's not running, if you drive up a mountain, the battery level goes down, indicative that you have burned a certain amount of that energy in the battery. Well, hybrid cars have something called electronic braking. You all aware of electronic braking? And this is a physics trick that is, and we don't quite have the tools to talk about here, but it's just a physics thing. Electronic braking is the process of using really clever ideas in how electricity works, and magnetic fields and electric fields and this kind of thing. If you are applying the brakes, instead of pushing two pieces of metal together, and as they slide against each other, creating heat, thus turning the energy of kinetic energy, the kinetic energy of your car's motion into just heat energy that dissipates into uselessness, right? Electronic braking takes the kinetic energy of your car moving, and it turns it into battery charge. It converts the kinetic energy of the movement of the car into, so you get less kinetic energy because you're braking, and you get more battery charge. All right, so here's the idea then, and of course, obviously, nothing's perfect, and there's friction, and et cetera, et cetera. But ignoring those ideas, if you're driving over a hill in one of these cars, right, going up the hill, you have to exert a positive amount of work. And so your battery charge goes down, right? Well, of course, that's what everybody can relate to. Right? Okay. On the other hand, once you start going down the hill, you're going to pick up speed. You can't pick up too much speed; you'll fly off the side of the road. So you've got to apply the brakes. Well, even though you apply the brakes, you still keep going down because, again, gravity, right? And so you keep going down, and as those brakes are applied, the electronic braking that's keeping you from going faster and faster is charging up your battery as you go down the mountain. So that's negative work, right? So it's just a negative work that only with recent technologies have we been able to really capitalize on. So as one of these hybrid cars is going downhill, it is recharging its battery. Said differently, it is expending a negative amount of work. So anyway, this is perfectly plausible now in this new context. So very reasonable thing and neat idea. Okay, so now the side note, the physics of how electronic braking works, we don't really quite have the tools yet. It takes, you have to understand electricity and magnetism. If you take a physics 2 course, I guess 152 probably does this kind of thing, and I don't know if they do that application specifically. But the ideas that go into how such a construction works, right? I mean, that's the little detail devil. How do you take car velocity kinetic energy and turn it into battery charge? That's not obvious. The necessary physics tricks for that are things that we're going to talk about in this course in a little while, at least to a certain extent. Okay. All right, so I just wanted to hit that negative sign before we go on. So now moving along, we've got these line integrals, and let me remind you, when we were talking about, let me go way, here we go. I made this observation a few days ago, that vector fields, on the one hand, you can think of those vector fields as representing forces. And that's what we've been doing when we've been computing work integrals, right? The whole point of these vector line integrals we created was we've got a vector field that's representing a force. And need to compute work, application. And so throughout all of that discussion that we've been doing, the vector field represents force. So now recall, I claim that it is also very important to be able to understand all the mathematical constructions from this course in this other context, right? A vector field could just as well represent the flow of a fluid, right? So reasonable question. We've got this new mathematical construction of a vector line integral. If I were to choose to think of that vector field as representing a fluid flow, what does that vector line integral mean? So in this interpretation, in this context, what is a vector line integral? And so I'm going to try to give you a good answer to that. I'm going to have to, sorry, I got ahead of myself. Okay. So we're going to have to lay a little bit of groundwork first, so bear with me for a moment. Now recall this picture, right? This is our usual picture. We have a curve. We're viewing the curve as being the image of a domain that we like better. Pull back, right? All that usual business. We have a little piece of the curve we're focusing on. It's approximately straight, but not quite. We've talked about this dx vector. Dx representing, two things. I mean, it's pointing in the direction that the curve is going, and its magnitude is equal to the length of that little piece of curve. And we've talked about the velocity vector. Right, in fact, the velocity vector is how we get our hands on dx, right? So dx is v dt. Okay, all right, so those are things that we've talked about. So here's a new, not exactly new, but here's a new to this conversation idea, and that is this thing. I guess I'll use blue, it's fine. That is the unit tangent vector. So we have talked about the unit tangent vector. It was a while ago, right? We were talking about curvature back in chapter 12, and it ended up being a useful tool for some of those things. So, quick argument about this. Notice that our dx vector that we already know is v dt, right? I can rewrite the velocity vector like this. Now, all I did there is I separated out from the velocity vector. Keep in mind the velocity vector is a direction and a magnitude. Right? The magnitude of the velocity vector being the speed. I just separated those out. Here's the unit vector indicating the direction, and here's the scalar indicating the speed. No big deal there, right? And then take these parentheses and just kind of regroup, right? Just do like that, right? Like so. And what can I say about this thing? V dt, speed times time. Well, that's distance. That's ds. Right? So what we end up with here is an alternative point of view on the dx vector. Previously we thought about the dx vector as being v dt. Now, and this is just different. It's not better. It's not worse. It's just an alternative. You can think of dx as being t ds. Okay. All right. So, here's our vector line integral that we were conveniently thinking of in terms of computing work. Now let's just plug in what we just showed here. dx is TDS. Yeah. Move some parentheses around again and notice that we get as our integrand now f dot t. And here's the weird thing. Now notice that our differential is no longer a vector. In fact, our differential is now the scalar line integral differential that we saw when we were doing scalar line integrals. Right? So this makes it look like a vector line integral is deep down somehow hidden in a way that we hadn't previously noticed, also a scalar line integral. Now, let me first sort of let me argue against that. Really, this is, I think, in a way, kind of an unnatural construction. dx is all about the domain. dx tells you everything you might want to know about the little piece of the curve. It tells you which direction that little piece of curve is going. It tells you how long that little piece of curve is. Right? dx is about the domain. So when we rewrite it like this, if we want to say, this is integrand and this is differential, then the problem is that, then the domain is kind of in both. Right? And so that's a little weird. I mean, in other words, sure, that's a scalar, but the integrand is not something that's separate from the domain. The integrand now includes something, namely dot product with t, that's intrinsic to the domain, not the vector field. Right? So I think this is a little awkward and weird. I don't want to exactly cross that out. I'm just going to kind of do like that. It's fine. By the way, this is the notation the book uses a lot for vector line integrals, f dot t ds. I don't know. I find it less appealing. I think this is more relatable and really notationally natural for my tastes. Okay. All right. So anyway, nevertheless, this is true. Flashback to early chapter 12. Dot product with a unit vector is a component. Y'all remember that? Way back when. T is a unit vector. So this is the t component of the vector field. And this point of view right here, this is an alternative interpretation of the vector line integral. This is what I claim will very reasonably interpret in terms of fluids. Remember, that was our goal, right? We've got this vector field that we had thought of as representing a force field. Now I want to interpret it as representing fluid flows. What is this? Well, it's this, and here's the interpretation that you can take. What you can say is that we're adding up over the entire curve, we're adding up to what extent does the fluid flow along the curve. Right? The F representing the direction and speed that the fluid is flowing. T component says to what extent is the vector field, to what extent is the fluid flowing along the curve then at that point, and adding up over the entire curve gives you, again, this total combined extent, you might say, to which the fluid is flowing along the entire curve. Okay. All right. Now, this hand-wavy discussion of how to interpret this, right, somewhat unsatisfying. I want to recognize that what we're accustomed to is having physical notions that we write down algebraic expressions for, and we write down exactly the algebraic expression that represents our pre-existing physical notion. And that's very comforting. That's how we often do things. So it doesn't always work like that. Sometimes you end up with the algebra first, and then you have to say, all right, well, given this algebraic expression, how am I going to interpret this physically? There might not be a pre-existing physical notion that this relates to, right? So that's kind of what's happening here. I mean, this algebra comes up very naturally, right? This isn't something that we have a pre-existing sort of sense of. This isn't something we've already given a name to in the physical world, but nevertheless, it is something we can make a plausible interpretation of, and so this becomes a new physical idea of interest. And by the way, it turns out this is useful in engineering, in studying fluids in the important ways that y'all will have to hear about more in those contexts. Okay, moving along. So every so often you get lucky. Look out. Oh, yeah, sorry, question. Yeah, go ahead.
So when we look at, like, this is going back a bit, so when we look at, like, f dot dx on the page when we say that it equals the dt of the dx part,
Yep.
Could, like, you also see, like, b as, like, the stretching factor from, like...
Yeah, kind of. Sure. I mean, sure. With taking that point of view, it's sort of, kind of. I mean, it's a vector, so it's not. It doesn't. It's not exact. I'm not relating a size to another size. Here, I'm relating the size dt of an interval on the t-axis with a vector dx that it represents both the size and the direction, right, of a piece of the curve. So, but it plays a role algebraically, kind of like a density. So, yeah, I encourage thinking of this as a modified notion of density. Absolutely. Yep. Yes.
Would both of these kind of ways of looking at like the vector
line
integrals,
yep,
would they both be valid for like a given curve?
Yeah, sure. So the point is, looking at a question like this, right? So this picture by itself, independent of the setup elsewhere on the page, maybe this vector field represents forces, and I'm interested in computing the work it takes, that I perform as I walk along the curve. Or, totally plausible, same curve, same vector field, maybe the vector field represents the flow of a fluid. Right? If this vector field represents the flow of a fluid, I could still ask, what is that line integral? And we now have a sort of a new interpretation, physical-ish interpretation of what that line integral represents. Yeah, totally. Yep. Okay. All right. Okay. Yeah. So every so often you get lucky on computing these things. So suppose you want to compute this line integral. Here we've got a curve. Let's see, I guess I'll zoom out one notch here. So this curve here is described by these formulas for how phi and theta vary over time. I'm on the surface of the unit sphere here. So if you're on the unit sphere, and if phi and theta are functions of time, then that gives you position as a function of time, and you can parameterize again by plugging in these formulas for phi and theta into the formulas for spherical coordinates. We're on this unit sphere, so rho equals 1. So that's a parameterization of a curve given in a weird way. Now, then I also have this vector field here. That's my vector field. Right, here's that curve. So the other participant in this line integral that I want to compute for whatever reason, that vector field, and at any point on this curve, I can draw what that vector field is. And how would I compute this line integral? So again, you can plug and chug. You can do the pullback, and you can crank it all out, and that would work. But it'd be a little unwieldy, right? So, like I say, every so often you get lucky. Here's the observation to be made here. The key observation is that this vector field is always a scalar multiple of the position vector. Here, let me do it like this, position vector. It's always a multiple of the position vector x. That means that the vector field is always perpendicular to the sphere. All right, so think that through. And we've got this, the position vector, of course, it's a sphere. It's the most symmetric non-flat surface that we know of. So the position vector is always perpendicular to the surface itself. Well, the vector field pointing in the exact same direction. That means the vector field is perpendicular to the surface. And because our curve is always in the surface, right, the differential is always tangent to the surface. And that means that this dot product is always 0, right? The dot product of those two vectors, one's perpendicular, one's parallel. That dot product's always 0. We're adding up a bunch of zeros here. So the integral's 0. No calculations required. Yep.
So is dx always perpendicular with the function in terms of like to give it? I mean, what was the logic behind why dx is always parallel to the sphere again?
Oh yeah, so the point is the curve is always staying in the sphere,
Okay.
right? And so if your curve is always in the sphere, then that means that your velocity vector has to be tangent to the sphere, and the dx is in the direction of the velocity vector. Yeah. Yep. So this example that we're seeing here is a peculiar thing, right? This is only because of the specifics of this example, right? I have a curve that's entirely within this surface. It's weird, right? And I have this vector field that is always, parallel to the position vector. That's not always going to be the case either.
Okay.
Yeah. Right. But like I say, every so often you get lucky. Yeah. Okay. All right. So heads up for this kind of thing. This kind of thing does come up again. My memories of ye old days as a second major in physics. It came up significantly, right? Not as much perhaps as I claimed earlier that 20% of the integrals I saw as a physics major were zero by symmetry, right? This not as often, but often enough that it's worth keeping one eye open. Always take a quick glance. Look for, is there something really geometrically nice about this situation? Just give it 10 seconds thought every time you look at an integral. And if it's not nice like this, well then fine, reject this, move on to other things. But give it a look. Okay. All right. Okay. So there's yet another kind of line integral that I have to introduce now. This is the third kind of line integral that we're going to talk about. It's a little bit weird that we have all of these kinds of line integrals, but anyway. Okay, so again, here's our little piece of curve. Right, and on that little piece of curve, we've talked about what the dx vector is. This is our differential of position, dx vector. Right, and you already know that dx vector, because it's a vector, it has 3 coordinates. Well, if dx represents your change in position, and if your position is given by coordinates, wouldn't it seem reasonable to say that the coordinates of that dx are just the differentials of those coordinates? I mean, in other words, if the purple vector represents your total change in position, the change in your x coordinate, well, dx, right? Old sort of convention of what to call that. And then, of course, don't forget, we know how to compute dx. Single variable calculus, old news. All right, so we have this point of view then So we have this point of view on what the dx scalar is. So this thing here, it's how much did x change along that? It's our differential, our linear approximation of how much x changes on that piece of curve. Sure. That's a fine point of view. No problem. But sometimes it's nice to have alternative points of views on things, right? So we talked about, for example, just going back to single variable calculus, right? Sometimes you want to think of derivatives as being slopes, and sometimes you want to think of derivatives as being, speeds, right? Sometimes you want to think of them as being factors, right? That's the change in the input times whatever to get the change in the output, right? That sort of proportionality. So different points of view that are ultimately the same thing, still very useful. You need to have multiple different points of view sometimes. Okay, so I'm going to give you a different point of view now on how to think about this dx thought of as the x-coordinate of the position differential. And it goes as follows, and this is going to seem really weird. So, and we're not going to make immediate use of this. But this is going to be really, really handy a little bit later on. This is extremely natural in important ways that will reveal themselves later. So here's the idea. We've got this piece of curve, let's say. Let's suppose that I were to do a projection of this piece of curve down to the x-axis. All right, let's look at the shadow of that piece of curve on the x-axis, and that shadow looks like this. And there are two things I can say about that shadow. One thing I can say about that shadow is how big is the shadow. That's one thing. Right. The other thing I can say about that shadow is that shadow going what I'm going to call the right direction along the x-axis, or is it kind of going the wrong direction along the x-axis? And here's what I mean by that. The piece of curve was going in a direction. Right? That orientation on that piece of curve, you could think of that orientation as giving you a sort of a direction on the shadow. Right? Just project the orientation, if you will, right down to the shadow itself. And notice that here, for that piece of curve, the direction on the shadow is exactly the same as the direction of the x-axis itself. Okay. All right, so we're going to say that shadow has a positive orientation on the x-axis because it's going in the positive direction on the x-axis. All right, so these two ideas combine to tell us what dx is. Dx is something whose magnitude is the size of the projection and whose sign tells you about the orientation of the projection. Right? So for this piece of curve here, dx is positive because of the direction, and it's this much. Sorry, my elbow hit the thing. It's this much because of the size of the shadow. Okay. All right. Whereas this other piece of curve over here, that piece of curve, it projects. If you push down to the x-axis, it projects to give you something of this size, right? But because along in here the curve is going that way, the projection is going that way. The projection is not going in the same direction as the x-axis. It's going in, you might say, the negative direction on the x-axis. So with that in mind, we're going to say that dx has magnitude equal to the size of the projection, and it's negative because it projected backwards. All right, now I don't think it takes too much persuasion to buy into the idea that this gives you, it's exactly the same. It's how much did x change? Right? So it is a much more it's a long way to go for an alternative to, we have this wonderfully crisp notion of what dx is up there, and here we have this clunky, awkward point of view of what dx is, and I claim they represent the same thing. They're the same thing. Right? So this is what you're probably much more comfortable with, I assume, right? But this one is going to be useful later on. So I want you to start kind of trying to absorb this alternative point of view on dx. Okay. All right, now we're going to set that aside. We're not really going to do anything with that at this particular moment. But proceeding along from here, dx vector has its coordinates, these coordinate differentials. These coordinate differentials we know how to compute. And now here I'm going to do something that we could have done a long time ago, but we never really quite got around to because, well, why would you? And here it is. It's a little bit weird looking at first, but I'm going to observe that, well, don't forget our vector field has coordinates. Recall we've decided to call those P, Q, and R. Very standard. Coordinates of the vector field. Our differential dx has coordinates, as we've just agreed, dx, dy, dz. This dot product, then, you could crank out that dot product, right? And again, why would you? How weird. Why would you want to take a nice, compact, crisp notation and expand it out in an ugly way to be much bigger and longer and clunkier? So that's why we didn't do it, right? But you could expand that dot product, and that becomes this, or so it would seem. And now we have to ask, what on earth do these things represent? These aren't things that we've previously defined, right? I mean, we've got to be careful with this. I mean, I can write this down because, well, I've defined it. That's a Riemann sum, right? These things over here, I have not defined up to now. I have not defined what I mean by integral over a curve of a function dx. Now, we've done integral dx before. Sure, no problem. Calc 1, old news. We've done integrals over curves before. We've never done them together. So this is a brand new thing. And so this, all I'm sort of getting around to saying is that we do have to write down a definition. This construction is defined by that. And then analogously for these. In other words, they mean exactly what you would think they mean. Dx just means dx dt dt. Everybody okay with that? Okay. So what you should be thinking at this point is, where is this going? How does this bias anything? What's the point to this? Why would I ever do this? Right? I assume that at this point, no one's seeing in the merits of this notation. Is that right? Like you can choose to write your line integral like this, or you can choose to write it like all of that. Okay. All right. So there's two good things about this note. Well, there's two reasons why you have to be aware of this notation. One is it's in common use. A lot of people like this notation, even though it's clunkier. So you're going to see it. You're going to experience it in your future engineering and other mathematical lives. So when you see this, you need to know what it is. If you see an integral written like this, that means this, and that means this, and that means this. So heads up. Okay. The other thing I want you to know about this is not just a clunky, pointlessly clunky notation. It turns out that this notation is actually pretty mathematically natural in some nice ways. If you want to take a more sophisticated point of view on multivariable calculus, this is a really good way to do it, as it turns out. All right. So we're not going to do those things in Math 212, right? So as far as we're concerned, this is sort of a cultural note. This is useful elsewhere, and y'all will probably never go there. Okay. So the main reason I'm showing you these notations is this other point here. You're going to see this notation in other contexts. Other people like it. And just remember, when you see this notation, right, you can just think, okay, fine. They mean this. Right? So just interpret it as vector line integral written out sort of one coordinate at a time in the dot product. Okay, so for example, if you see this thing right here, and the first thing that should occur to you when you see this notation is, hey, that's weird. we're adding up over a curve, but on each little piece of curve, we're not multiplying by the size of the piece of curve. We're not doing a dot product with the differential on the piece of curve. We're multiplying by just one of the coordinates of that differential. The curve is going every which direction, but we're only using as a differential how much it's moving in the y direction. So the first thing that should occur to you is that's weird, right? And then you recall that this is one of these new kinds of coordinate line integrals, as I like to call them. And so you see this coordinate line integral, and you should then say, okay, what vector field is it that dot product with dx gives me this thing? And you can kind of reverse engineer it, and you think to yourself, well, dx, of course, let me scratch this out. This dx is dx, dy, dz. And so the only way I can get g times dy is if g is the second coordinate of this vector field. Right? That makes sense to everybody? No? All right. So this section is, like I say, this section is pretty much just a liability for you guys. This isn't going to help you compute stuff. This is just going to help you understand notation that you will unfortunately see elsewhere. Okay. All right. Okay, so quick summary of different notations for vector line integrals. Here's the notation that we started with. There's lots of nice things about this notation. It's, if nothing else, I think it's very simple and elegant. You look at all these other notations for vector line integral. This one requires the least amount of pencil lead. That's convenient, right? It's quick and easy to write. It relates very naturally to work, to one of the big physical applications that we do with this construction. How do you compute work? Well, work is force dot displacement. So that's a really, it's just right in terms of how it's written down. It looks just like the application we're using it for. That's wonderful. Right? And I've made this observation already, but let me do it again. It's geometrically natural. In other words, so we're looking at a little piece of curve. The dx vector encapsulates all of the relevant information about that little piece of curve. Dx tells you what direction is the curve going, and by its magnitude, it tells you how long is that piece of curve, again, in our linear estimate. Okay, so this is my favorite of all the notations. If I had to pick one, that's my desert island vector line integral notation, right? Now, but there are these other notations around here, right? So, the very first thing we proved is this right here, that if you want to do a pullback through a parameterization, well, here you go. So this is another way that people could write vector line integral, and it's very convenient for direct, plug and chug computation, which is nice. Okay. There's these two notations. Again, they all represent the same thing, right? These two notations are conveniently relatable to fluid flow. And they also are sort of, I'm going to say, consistent with scalar line integral notation. If you want all your line integrals to kind of look the same, there's that. To me, that's more of a minus than a plus. I want mathematical objects that are fundamentally different to look fundamentally different. Let's not conceal the differences. Let's make it apparent what the differences are. Right? But anyway, there's that. And then we have this last notation that we were just talking about, and again, it's in common use. So heads up, be prepared for it. Okay. All right. So this is just kind of a quick summary page. Okay. So now we're going to enter into some of the really fun stuff in Chapter 15. It's where it gets kind of exciting, to me anyway. This is my favorite stuff to teach in the course, and it relates to the fundamental theorem of line integrals, and to the fundamental theorem of calculus. Relates to the fundamental theorem of calculus, and I know that y'all all know the fundamental theorem of calculus, right? Let me correct that. Make sure that you know the fundamental theorem of calculus, all right? And by the way, when I was a high school student, I will confess I did not know what the fundamental theorem of calculus was. I knew how to do integrals And I knew, you do the integral, and then the numbers at the top and the bottom, those are the things you plug in. And I could do it. I kept getting good scores on my test. But if somebody asked me, what is, as a theorem, state as a theorem, the fundamental theorem of calculus, I couldn't have done it, right? And I was a strong high school student, right? So if you are not 100% clear on what exactly is the fundamental theorem of calculus, come to my office hours. Let's talk about it. And you're probably going to think, oh, that thing, right? But it's nevertheless a good idea to have a crisp, clear idea of exactly what are the things that we give these names to. All right. So what I want to do is talk about the fundamental theorem of calculus a little bit. The reason why is we're going to see a bunch of theorems here in Chapter 15 that are very, very similar to the fundamental theorem of calculus. They're highly analogous. It's sort of like they are the fundamental theorem of calculus in these other contexts. This is a pretty big deal, right? So I want to make sure we're all not only really clear on what the fundamental theorem of calculus is, but I want to take a point of view, a specific point of view on the fundamental theorem of calculus, designed to serve as a template for how we're going to take different points of view or analogous points of view on these different theorems. Right? So we're going to do the fundamental theorem of calculus here a certain way, not because this is the easiest way to prove the fundamental theorem of calculus. I don't think it is. But because this point of view on the fundamental theorem of calculus will give us a foot in the door, a sort of a starting point for getting to these other theorems in a way that's I think really valuable. Okay, so hopefully you have seen at least some of these constructions I'm about to show you. If not, let's just choose to look at it in this way. Okay, so normally we think of the fundamental theorem as how to compute integrals. I don't want to. Let's think of the fundamental theorem as how do you compute f of b minus f of a. All right, seems like a weird thing to want to do, but let's suppose I wanted to compute f of b minus f of a. By the way, we need f here to be continuously differentiable. I don't want to worry about regularity. So for pretty much the rest of this chapter, yes, we need for the functions to be sufficiently regular, and that's very important in a higher level class than Math 212. In this class, it's just going to be a distraction. So anyway, I'm just going to say that. Assume everything is sufficiently nice, and we're going to sort of go on from there. Okay, so how do we compute f of b minus f of a? First observation, I can interpret this expression. That's not just some random algebraic expression. That's something I can think of as a thing. Change. Right, we're keeping track of how much does this function f change over an interval. So I'm just going to call that change. Right? Okay. Next big observation. This is a big one. This quantity is an accumulating quantity. And I'd like to talk about what I mean by an accumulating quantity. There are certain quantities of interest in math, physics, engineering, economics, whatever, that have a certain feature of accumulation. And other quantities, also of interest, just don't. So here's a couple of examples of accumulating quantities. I just want you to know what we're sort of talking about here. Let's suppose you have a metal rod on the x-axis, and something like that. And again, the density is not constant. You want to compute the total mass inside of there. The total mass that I associate to that interval in terms of, on the rod. The total mass is the sum of the little masses that you would get if you could chop that up into little pieces. Right? So the total is the sum of the equivalent quantities on these smaller intervals. So on the big interval, I associate all of the mass. On this little sub-interval, I associate just that little bit of mass, but if I add up all those little bits of mass, then I get the total mass. So this is what I mean by accumulation. And you might be thinking, well, isn't that just, how does this not apply to, isn't that a universal concept? Well, no, not quite. Here's a counterexample. Centroid. does not accumulate, right? The centroid of that interval is simply not the sums of the centroids of all of these little pieces. If I take all of these values that are the centroids of those little pieces, if I add them up, it's going to be some enormous number. It's certainly not going to be the centroid of the piece, right? So centroids do not accumulate on intervals. Mass does accumulate on an interval. Everybody see the difference? Okay, so this is a really important feature for a quantity of interest to possibly have, and mass has this property, and change has this property. Change it behaves kind of like mass in a way. It's got this accumulation. It's almost like it's a kind of a stuff. You can think of mass, of course, as a kind of a stuff, and it is because it is a physical stuff that when you subdivide, well, look, we're not going to make this physical stuff just disappear, right? The subdivision is just sort of a reorganization, but that accumulation is because of the fact that it's kind of it's stuff. You know what I mean? Change, mathematically, behaves just like that. It's like change is a kind of a stuff. All right, now, again, you didn't see that in a Calc 1 class, I know, right? But it turns out to be a really nice point of view on the fundamental theorem. So I want to make the observation here that change is an accumulating quantity. Here's how we write that. Change on the whole interval is just the sum of all the changes on the little bitty intervals when you slice it up. Right? There's that accumulation feature. And now I'm going to throw a limit out front because that's free. Let me explain why that's free. We have an expression here, and let me zoom for focus. We have this expression. We're adding up. I goes from 1 to n. Right? We're chopping up the interval into n different pieces. For every value of n, we get exactly the same value here. Right? It doesn't matter what n is. Change accumulates no matter how many pieces you chop it up into. So this expression here is a constant function of n. And if n gets bigger, this expression doesn't change. If n gets really, really big, the expression doesn't change. It's just constant. And so, of course, if I take a limit as n goes to infinity, still the same. Okay. All right. So you look at this expression and you start to notice, wow, that's kind of vaguely suggestive of a Riemann sum, but there's no sort of dx over here. If I want this to look like a Riemann sum, so I can say integral, I need to get a dx to show up. How can I get a dx to I can't just stick it on here. That's not fair, right? But I can do this. I can both multiply and divide by the same thing. That's legal. And now I've got what's going to be my differential, and this really does look a lot like a Riemann sum at this point. And so, let me zoom back out. This becomes an integral. Right, the integrand, as I'm taking the limit, and by the way, I want to fully recognize there are some formalities here that I am sweeping under the rug. It's not what we need to worry about in Math 212. Don't worry about, I'm going to assert that I can take this limit and just kind of put it on the inside there. Again, it's not an issue for us. But in the limit, as n goes to infinity, perfectly plausible, I think. The limit of delta f over delta x is the derivative. Yeah?
On the vector side, why does the delta f turn into nabla?
Where is this? You on the next? Are you on the next page? You might inadvertently be on the next page. Yeah, the next page looks a lot like this page, and that is on purpose, but not because I wanted to fool you. Sorry, that was inadvertent, right? But because I want the theorem we're going to see on the next page is I deliberately want to make it apparent how very much like this it is. Yeah, exactly. Yep. Easy mistake to make. Okay, yeah. Yeah, question, yeah.
So how can you just add the two delta x's?
Oh, well, I multiplied and divided. Right? Yeah, so it's like if I want to multiply and divide by 6, perfectly legal. Right? So it's like together, these are, multiplication by 1. Yeah. Okay. All right, so we're done at this point. Remember, we were computing change, and what we found is that we can compute that change as an accumulation. The accumulation I rewrote as an integral. The integral has this integrand that I'm familiar with. And here's a weird sort of additional point of view. Now, again, remember we decided to think of change as being a kind of a stuff. It's vaguely physical, right? It accumulates like physical things, right? So, by analogy, if I were to write this, right? This is the analogous accumulation integral for mass. This being mass, right? What do we call this thing here? We call it mass density, right? Because that's mass. In the same way, then, we're computing change accumulates just like mass does. By that analogy, if we're going to call that mass density, it would seem reasonable to call the derivative change density. Which, again, kind of weird, right? But we're thinking of change now as being kind of vaguely sort of physical. And so when you have a vaguely physical thing, you can talk about how much of that stuff there is per unit size and thus a density. We'll talk more about this next time. See y'all later.